Okay, so just to recap quickly, we've cleared the screen, cleared the variables, set up a site ID, we've loaded in the data, displayed it first using NC display, then use NC read to read it in, and then we've plotted the data. So we can see all of the data. Now this is total water level, which includes the tide, the surge, the mean sea level, everything. Okay, now what we're going to do now is do a tidal analysis. And what we're going to do is we're going to use a tool called utide, which is some built-in MATLAB functions. Now what's really nice is MATLAB has a fantastic community that writes functions. So this is utide. You can read all about it. This is written by a person called Daniel. You can download this toolbox. So we've downloaded it there. Now what I'd encourage you to do is, so go to downloads, there's utide. What I'd encourage you to do is put that in your folder. What I would probably do is just put it in the base directory here, utide, or if you wanted you could put it, actually maybe it's better to put it into code, but you can put it in wherever you want. So utide there. And you can see it's got a series of functions here that you can use. There's also quite a useful report that tells you about it. So Daniel is from the University of Rhodes Island and tells you all about the software here. Okay, so what you need to do now is you need to set the path. So if you go back to MATLAB Home, you need to set a path here and you need to add the folder. And what you can do is just add that utide folder there, save it, close. So now that's set. So if we call these two functions utsolve or utreconstruct, it knows where to find them. Okay, so now what we are going to do is do a harmonic analysis. And obviously you've learned about it this week, but first of all what we need to do is find the data that lies just within a given year. And we're going to use 1996 because that's a year when there's lots of good data. You can see a nearly complete data record. Okay, so what I'm going to do is I'm going to say I is find ts greater than or equal to, use the datetime function, and I can find 1996, sorry, this should be greater than or equal to 1996, 11,000 for seconds, and ts, that's here I don't use equal to, but just less than, date time 1997, 11,000. Okay, now this should tell me the row numbers, so it'll be a logical array. Zeros are where it's not. If it's ones, it does equal to 1996, and there will be some ones in there somewhere. Okay, now I'm going to create two new variables. I'm going to say ts 1996 is equal to ts and just the I rows, and I'm going to say, again, cut and paste if it's easier, water level is water level. So this now is just the data for 1996, and if it's hourly there should be about 8,784 values depending on if it's a leap year or not. So now we have the data just for 1996. Now we can use the function. Now every function has square brackets for output, and the function is called utsolve, and then we have inputs. So the first variable is going to be the date and time. The next variable is the water level. And then we have an empty variable. If you look up the help utsolve, it kind of tells you what to do, or you can look at that PDF and it'll give you some examples as well. But up the top here, it should tell you what is needed to solve this. So we have one-dimensional data, so we don't need that variable there. Now, one thing to remember is that usolve is a bit of an old function, so it doesn't use date time. So we need to convert the date time into what's called a date number using the date num function. Now we're just going to put two other variables on here. We're going to use the function auto, which in the menu you can read about what that does, and we're going to say that the data has no trend because it's only a year of data. And what it's going to give back to us is tidal coefficient, so we can run that there. Now it will take a little while to run this data set. So we just need to be patient. It's doing quite a bit of complicated mathematics statistics there. Okay, so here we go. So here you can see, or if we click on TA, we can see we have the name. So these are each of the different constituents. M2 is the main one, main lunar, main solar. These are the diurnal ones once a day. And for each one we have an amplitude. So M2 is the biggest, so that has 1.8 meters. S2 is the next biggest. We also have a phase, G, and we have uncertainty, the confidence intervals around the amplitude as well. Okay, now what we're going to do is, let's go down to the next step. Now we're going to create a table function, call it T. This is just a nice way of explaining, so we're going to have TA coefficient, and the first thing I'm going to put in there is the name. Then we're going to have TA coefficient, and we're going to put in the amplitude, which is A, and then we're going to have TA coefficients, and we're going to put in the phase. And then we can have the variable names function, and here variable names, and here I'm going to put the square brackets, but we can add in the double. We're going to add in the name, amplitude, and phase. Okay, and we're going to run that. And this is just a nice way of exporting the data so we can see it in a nice format. Oh, sorry, I ran the code again, so it's just redoing this, which is a bit slow. Okay, so there you can see M2, it orders it by size. So M2 is the largest, and S2, then K1. If you do another site, you'll see that these orders change. Okay, normally around the world, M2 and S2 are the biggest. In diurnal regions, K1 and N1 might be the biggest. Okay, now what we're going to do is I'm just going to create a variable called TA. All of the rows, column 1, is equal to TA coefficient.A, the amplitude. Okay, and then what I'm going to do is the second column is going to be the amplitude, so that's what's stored in TA column 1, and I'm going to divide that by the sum of the amplitudes, and to get it into percentage I'm going to times everything by 100. Just going to check that I've got my brackets right. I might need an extra bracket, but let's run that. Okay, so that looks good. So now I've got a percentage. So the M2 amplitude is 1.84, but it makes up 34%, 10%. So you can see that most of them are just in the largest constituents. And then finally, I'm going to do a cumulative percentage. So here I'm just going to use the sum function on column 2, and it's going to add them all up for me. So I'll just run that again. It takes a little bit of time. Okay, now we can produce a plot with 3 plots again. So I'm just going to actually just nick this code again, scroll down, get the next tile, and actually on the end there, let's get the axis size again. Again, you can see when you get good at MATLAB, you can actually do things very, very quickly. Now what I'm going to do is, rather than the plot, I'm going to use the bar function, and here I'm going to plot TA just column 1. I'm going to take out the here, so I'm going to have a level. I'm going to keep the title in there. Okay, now I'm just going to run that section again. It will be a bit slow because it's doing the usolve again, but let's just run it. And then what I'm going to do here is set the xlim And what I'm going to do is this is 1 to the length of TA shift column 1. So it's going to go from 1, and there is 67 constituents. Okay, then I'm going to set the X ticks. So at the moment they're every 10, but I actually want them every 1. So I'm going to go from 1 at intervals of 1 to the length. And then I'm going to set the X tick labels as being the TA coefficient dot name. So we can run those there. So hopefully what you'll see, you'll have 1 to 67, and then replace it with the actual names. So you can see the M2 is the biggest one, that dominates 1.8, S2 is quite a bit smaller, all the other ones are much, much smaller. Okay, now TA, I've done that wrong, coefficient of name, we can run that again, and to check that that works. So again, if you get any red code, just read it, and it normally will tell you, oh, I've made another mistake here, it should be labels, so I probably want to stop that and just run that again. Okay, so now you can see, yep, it's plotted all of the, and it does it in order of size, which is really nice. Now what we're going to do is I'm going to cut that and paste that again, but this time I'm going to plot the second row, and here it's going to be a percentage rather than a level. Oh, this should be meters, so change that to meters, and then I'm going to plot the same again, but this time it's column 3, and this is going to be a cumulative percentage. Now what I'm going to do as well is plot a line. So actually I can use the function yLine, and I'm just going to plot it at 90%. I'm going to have a dotted red line. I'm going to make the line width 2. Okay, I've made a mistake now. Oh, here this should be column 3. So again, don't worry about mistakes, you know, click on it to read indexes. So it says there's only 2, but I've specified a 3. So you run that again. I overwrote it by mistake. So you can see that, you know, I've been using MATLAB for 20 years. I still make mistakes easily, but you know, it's relatively easy to correct once you know what you're doing and working it out. Okay, so there you've done your first tidal analysis. And you can see that these are each of the constituents. If you put in more data, you'd get more constituents, but by default, a year of data will give you 67 constituents. And here you can see that actually the top 20 or so constituents make up almost 90% of the data. So actually you can get 90% of the tide just with your kind of top 20 constituents. Okay, what we're going to do now is find row numbers. And we're going to use the string CMP function. So we're going to search within the variable the name, and we're going to look for when we have the K1 constituents. So we can run that. And you can see the K1 is name, it's a third one down. So you can see here you have 001. So we know that that is row 1. So what I'm going to do is just going to copy this 3 other times. I'm going to change that to 2, 3, 4. And here we're going to have O1, M2, and S2. So what we're going to do is calculate the tidal range and form factor. Okay, now remember the form factor is the amplitude of K1 plus the amplitude of O1 divided by the amplitude of M2 and S2. So what I'm going to say is form factor, it's going to be TA coefficient dot amplitude, and on row number R1, so K1 would be row 3, cut and we're going to add this, and this time it's going to be R2. So these are your two diurnal constituents, and then we're going to divide, and we can copy and paste these again. But this time we're going to have M2 and S2, so we can run that. Dot indexing is not supported here. What have I done wrong? Oh, it's not dot there, it's understroke. So remember, so again, you know, it's easy to make mistakes, but often you can just go through and correct them. So it's the variable name, and then within the variable. Okay, so here it says my form factor is 2.6, and that is mixed, but very close to the semi-diurnal record. Okay, what I'm going to do now is use an if statement to work out the tidal range. So if you've never used an if statement before, you can type help if here and see how it works. But what I'm going to say is if the form factor is greater than 1.5, I'm going to use a certain equation, else if the form factor is greater than or equal to 5, end. And now we're going to do the tidal range. So the tidal range is if the form factor is sort of mainly semi-diurnal, then we just use the M2 and the S2 constituents. So the M2 is 3, so we can add the M2 plus the S2, and we multiply everything by 2. Okay. If the tidal form factor is mainly diurnal, then we use K1 and O1. Now, M2 is always large in the world, so if it's diurnal, we also add M2, which is row 3 there. And again, we multiply by 2. So the tidal range here is 4.77 meters. Now, you can just go back and check this in the figure. You can see it's more than 4 millimeters, but assuming that here we're only using the 4 main constituents, you can see it produces a relatively good approximation of what the tidal range is.